Hey everyone, good afternoon. Today we'll be going through our technical talk this month of August. And our technical talk will be on data science and digital engineering in the petroleum industry. And our guest speaker for this technical talk is Ms. Kadija Hassanali. I would like to just thank everyone for attending this technical talk and being here today. And I would also like to just thank our guest speaker, Ms. Hassanali, on taking time out of her day to be here with us today. Just some ground rules. Please use your full name so that you can be easily identified when asked to speak. Please always keep mics off during the technical talk unless when asking questions. The use of camera for this technical talk when asking questions would be preferred, but is not mandatory. Please remember to never share the meeting info with anyone outside the registered list of attendees. And just a general reminder that this session would also be recorded. So now on to the topic of data science. The oil and gas industry has become more technologically advanced through the implementation of data science and digital engineering as a key component in the industry. A data scientist is someone who uses techniques such as machine learning and artificial intelligence to extract data on future patterns and behaviors based on the analysis of past and current data. The oil and gas industries are currently reimagining data science and its applications of uses to the industry. These include remote sensors in exploration, drilling, production, and seismic operations to logging while drilling, which allow data to be recorded in real time. In today's technical talk, our guest speaker, Ms. Hassanali, has a vast wealth of experience in this field and will give us a bigger picture on the importance of data science in the industry. About the guest speaker, Ms. Kadija Hassanali has a BSc in Chemical Engineering from the University of Delaware and worked as a reservoir engineer with ExxonMobil, supporting onshore and Gulf of Mexico fields. She completed her MSc in Reservoir Engineering at the University of the West Indies and joined BPTT as a data science challenger in 2018. Since then, Kadija has supported data science projects across the organization. She has seen firsthand the material impact that leveraging data insights can make in the energy industry. Now, I would like to pass on the presentation to Ms. Hassanali to present us on this key element in the oil and gas industry.
Thank you very much. I thank you for the introduction. I will definitely say my knowledge is not that vast. I guess as you can tell from my bio, I've been doing this for a couple of years, and I have seen, data science being applied in the oil and gas industry, but by no means am I, an expert with years and years and years of experience. But I will do my best. So today we're going, and I should also say that it's a pretty informal presentation. So, if you have a burning question, do feel free to stop me. Just feel free to ask any questions. Right, so the topic I'll be talking about is data science in digital engineering and digital engineering in the petroleum industry. And Jordan alluded to it, in the beginning, but I think there's a lot of misconception about what data science actually is. You can see these memes, it's funny, but it's true, there's still some misconceptions about what data science is and what data scientists actually do. So Harvard Business Review in 2012 called it the sexiest job of the 21st century. Unfortunately, the models that you work with look like this rather than anything more attractive, unfortunately. But seriously, what is data science? So it's the art of turning data into actions, right? So the goal of data science is to gain insights and knowledge from any type of data. And that is what distinguishes it from kind of more academic pursuits. The fact that, you know, a data scientist in a company is expected to generate insights that will have a material impact on the organization. Now, I know I refer to types of data here, structured versus unstructured. And so you can think of structured data as the type of data that can be held in a table. So you think about things like numbers, dates, strings, which are just characters, for example. If they can fit in a table, then it's most likely structured data. Unstructured data is the types of data that you would be familiar with and come across a lot in the oil and gas industry, right? So it'd be things like images. When you think about, for example, you know, seismic images, it might be things like video, and I'll show you all later on in the presentation, for example, a video that's been analyzed in order to look at the size of the cuttings on a shale shaker. So in the oil and gas industry, we do come across a lot of unstructured data, which in the past has been much more difficult to deal with. And data science really allows you to unlock the potential from unstructured data as well as structured data. But getting back to, you know, data science and what data scientists do. So data science, you basically generate those insights that will impact the business by creating data products that will help a business to generate revenue, optimize costs, reduce risk, etc. And then you might ask yourself, okay, so what is a data product? It's any application of data that has value to the business. So Jordan mentioned in the intro that data scientists use data, for example, to predict a phenomena based on past and current data. That is 100% one of the things that data science allows you to accomplish. But then you may also have descriptive models or models that give you insights. So for example, it may not be where you're predicting a phenomena, but data science is allowing you to understand why that phenomenon has occurred, or it might tell you something between, you know, the relationship between two things. Like if you're thinking about a refinery, it might be the relationship between average temperature and pressure in your coker, for example, and the probability of producing short coke, which is an undesirable product. So it's not just prediction, it could be descriptions or insights related to how things how phenomenon come about, or things like that. And I guess the other thing is, why is it so popular now? And I should say that data science wasn't really a real thing before 2012. And then all of a sudden, everything is data science, this, machine learning, that, artificial intelligence, all that. But it's directly as a result of a couple of things. So one is just how much data we all, on an individual and also on a company level, how much data we produce, right? So there's a statistic that says that 1.7 megabytes of data is created every second by every person during 2020. I mean, that's incredible. And then you hear things like, you know, in the last 2 years, 90% of the world's data has been created. I mean, that's a heck of a lot of data. We see here 2.5 quintillion bytes, which is 10 to the 15 bytes of data are produced by humans every day. You know, at the end of 2020, 4.4 zettabytes will make up the entire digital universe. So these figures really are quite astounding. And then if you think about, you know, in your personal life, how many tweets do you tweet? You know, how many pictures do you post on Instagram? Like, on a personal level, we generate so much more data. So it's the combination of generating that much data, and then the fact that we now have the technology and the computing power to process and analyze all that data. So those two things are like the perfect storm that has brought data science to the forefront. in recent years. And then the last thing to highlight, what things kind of make up data science. So it really is a combination of computer science and IT skills. So that's, coding, software development, etc., machine learning. It's that combined with math and statistics, because the machine learning algorithms that you apply are all based on, fundamental statistics principles. And that's why you see a lot of people who have background in statistics, for example, get into data science because it's sort of a natural progression. And then the last one is domain knowledge. So it's important that, if you're working as a data scientist in a particular industry, that you have some sort of knowledge about that industry, because it will help you better formulate your data science questions or conduct a data science project if you understand what that industry is about and what that data is actually referring to. So domain knowledge is also quite important. Okay, so what does a data scientist do? The answer is a data scientist, that the job doesn't look the same for every person. It's very different day to day, I guess, depending on what industry you work in. Even within a particular industry or even a particular company, it depends on a lot of factors, so that the day may not look the same for everyone. However, there are some there's some fundamental parts in the data science process that a data scientist will do as part of the job. So, first thing kind of makes sense, acquire or obtain the data that you need, which sounds simple in theory, but acquiring good quality, and I say that with quotation marks, but acquiring, good quality data, maybe financially, cost-wise, may be expensive. Logistically, it may be hard to acquire data. If you think about in the oil and gas industry, for example, it's logistically and financially costly, for example, to obtain logs or seismic, so obtaining the data could potentially, pose a barrier. I guess while I'm speaking, you can actually look at this chart, because it shows you the effort that's required for each of the 4 steps. So the second one would be, prepare your data. So manipulating the data to fit your analytical needs. The data may be of a quality where you can't work with it. For example, there may be missing values. So then you might need to apply certain techniques to be able to impute, i.e. fill in those blanks for the data. For example, if you're working with images, you may have to do some pre-processing of the images. For example, you might need to convert a color image to a grayscale image and sharpen edges, etc. So you do need to prepare the data, and as you can see, that there's kind of escalating effort required for that step. The third one would be analyzing the data. So you can see that this is a step that is the most labor intensive, and you can also see that it's iterative. So you would use supervised and unsupervised machine learning techniques in order to analyze the data, to get your insights from the data, to come up with your predictive model, if that's the case. And it's iterative because you would, as a data scientist, you'd be working with domain experts, for example, and you would go back to them, after you tried a different approach, and see what they say, get their insights, kind of make sure everyone is aligned, and if not, go back to the drawing board. That's why it's an iterative process. And in terms of when I say machine learning, it's exactly as it sounds. It's really the process of trying to get a computer to learn from data without it being explicitly programmed to do so. And when I say supervised versus unsupervised machine learning, in supervised machine learning, your data has labels. A good example of this would be if I want to have a if I want to train, for example, an algorithm to recognize the difference between a cat and a dog, or to classify an image as a cat or a dog, I would give it a lot of labels, a lot of images of cats and dogs that are labeled, this is a cat, this is a dog. So that's an example of supervised learning. In unsupervised machine learning, you use unlabeled data. So an example of this would be, let's take the same cat and dog scenario, but in this case, I'm not going to tell the computer that, or the algorithm, that these are images of cats and dogs. I'm just going to give them all the images and see if it could recognize patterns in the images that would help to distinguish between cats and dogs. So that's the difference. And then the last step would be acting. So turning data into actions. Now, they have the degree of effort for the, I guess, for the data scientist, the degree of effort is probably not, like you could say, maybe your job stops at, okay, you've given the stakeholders your feedback, you've given them your model, etc., and it's for them to do whatever they will do with it. But I guess in the context of an organization, deploying a data science solution across the business, for example, does require a lot of effort. And I guess the other thing is, if you don't act on the insights that you generated from your whole data science project, what is the point? If you do all that work and then you don't act on it, what is the point? Because you've spent money, you've spent time and effort, and the business has nothing to show for it. So the acting part is important. And that's why I have here that actionable, impactful insights are the holy grail of data science, in that it really should have a positive material impact on the company. So now we get to the nitty-gritty and why we care in terms of an SPE talk. So data science and analytics in oil and gas. So I saw this quote a couple of years ago, and it really resonated with me. And I'll just read it. Well, some of it, it's bringing analytics to bear on the complexities of, in this case, they were talking about, shale, for example. But, it could potentially allow you to optimize the production process and double the number of effective stages, thereby doubling output per well and cutting cost in half. So yes, they're referring specifically to shale production and development and all that. But I mean, it's incredible that by kind of using data science and data analytics, that you could potentially double the output of a well and simultaneously cut the costs in half. To me, that is incredible. And I guess the big takeaway is that the industry produces a lot of data. And if we're already producing a lot of data, then what really do we have to lose in trying to kind of extract as much insight as we can out of data that we already have? It's kind of a win-win. Anyway, but let's going back to this data science and in oil and gas. Why is this a thing? Why in oil and gas, are we seeing the implementation of data science techniques? And a big part of it stems from big data. The oil and gas industry generates a ton of data, and from your studies, you absolutely would see that. So when we refer to big data, we're talking about data with these 5 attributes, right? So think about it. One of them is volume, just the sheer size of the data. Think about an exploration, in seismic data acquisition, which is sometimes the first set of surveys that you do, the seismic surveys on on a particular block or whatever. It generates a large amount of data that will be used to develop, your images of the subsurface layers. When you think about drilling, we have drilling tools now that allows you to transmit huge amounts of data real time during drilling. And we have things like logging while drilling and MWD, which you're transmitting various types of data and various data to the surface real time. We also have during the production phase of, of development or whatever, where you have sensors, optical fibers that are used in wells to record different parameters. Again, basically real time things like, temperature, pressure, composition, etc. So just the sheer volume of data that the oil and gas industry generates is substantial. Another characteristic of big data would also be the variety. And again, think about the different types of data that we generate. So things like logs, for example, or like if you're talking about seismic images, those are images, but then we also have things like video. Again, I'll show you the shale shaker video that I have coming on to the end of this. You also have things like audio, for example. If you're looking at like acoustic sound detectors, for example, it might be sort of an audio signal that gets transmitted, text. You think about old-fashioned drilling reports, for example, or even kind of digitized text. I mean, all the reports and stuff that are generated, just a wide variety of data. When we talk about veracity, we're talking about the truthfulness of the data, and I guess the assumption is take it with a grain of salt. But the data from these sources that I just described should be truthful data. It should be the data that you can trust. Again, grain of salt. Take with a grain of salt. Right, and then when we also talk about the velocity, we refer to the velocity when we talk about big data, right? So processing the large amounts of data that's generated in the oil and gas industry, for a human to do it would be impossible, right? However, there are many cases where you need real-time fast processing of data. Think about, again, in drilling a well. You need to be able to process all of the data that's coming to you from the sensors in order to be able to predict a kick, for example, and prevent a blowout. So there are cases when the velocity of data is necessarily quick and you need to be able to analyze the data at that same speed. And then, of course, the last thing about big data is that it's valuable. And I hope that from kind of the scenarios that I've described when talking about the other four characteristics, that it's clear that the data is valuable. I mean, again, just going back to exploration, who is really going to drill a well offshore, for example, without seismic data? So these things this type of data is critical to making decisions in the company. Right, so now data science and analytics in oil and gas continue. Here, what we're looking at is it's sort of the benefits, and I kind of alluded to them in the last slide, but when we think about using data science and data analytics, we think, okay, these procedures could be real time and very cost effective. So one thing that surprised me, I guess, when I started this, as a data science challenger, is the fact that it's very, and I didn't know this before, but it's very expensive to store large volumes of data. I had never thought about it before, but if you think about like cloud storage, for example, these companies are paying exorbitant yearly fees to be able to store their data, both physical data and of course digital data. We think about, I guess, and because of that, as I alluded to before, it makes no sense to not try and use that data in order to generate insights that will benefit the company. Big data analytics and data science will allow for near real-time visualization and alerts and also storage of these large data sets. So an example of, kind of a real-time application might be using machine learning to interpret ASD signals, which an acoustic sound detector is a piece of kit that will allow you to detect sort of sounding events. But it's very difficult, for example, for a human and impossible at a real-time level to use these ASD signals to, you know, predict that, okay, a sounding event is probable. Computer vision, for example, which is where you exactly as it sounds, you're teaching a machine how to quote unquote see an image or you know, assess an image. So using computer vision will allow you, oh, sorry. Okay, this is actually a typo. Please ignore this. But basically it's where, you know, using machine learning will allow you to basically process these ASD signals real time to determine whether or not a sounding event is likely to occur. Right. The second thing is reduction of risk and better decision making. So data science can help reduce risk and help in learning more about geological subsystems, for example, which increases the accuracy of decision making. So a good example of this would be using machine learning to automate depositional element prediction. And in using kind of this automated technique, where it would take a human, for example, weeks to pick out, you know, to analyze all the data and pick out depositional elements that may or may not be present, the quickness of this automated technique will then allow you to generate multiple models, right? So then you're basically capturing, or you're better describing the uncertainty involved, which will allow you to make better decisions. Another kind of example of, you know, how to reduce risk and make better decisions would be using proxy models, for example, which will allow you to, a proxy model basically allows you to model like a really complex problem in a much easier way and is much faster to compute results. And so you use a proxy model, for example, to predict water breakthrough timing and also post-water breakthrough performance, right? Which is, very, very critical step in managing a reservoir, right? The third thing would be increased accuracy in drilling methods and oil exploration. So data science can help optimize subsurface mapping of drilling locations. It could indicate where it would be best to stay the drill bit, and it can even optimize the logistics. So, for example, rig timings. You know, there are data science applications for all of these things. An example in this space would be, again, that this kind of a similar idea of using proxy models to model complex engineering concepts, for example, like drilling. And then once you build that proxy model, you can actually use the proxy model to optimize things like the ROP during drilling, for example. And then the final aspect I have here is ensuring efficient machine performance. So, and I'm sure you know this, but machines have sensors, or a lot of the kit offshore on platforms, or, you know, onshore in refineries, for example. These pieces of kit have sensors that, you know, transmit sort of parameters like temperature, pressure, composition, etc. Data about their performance. And in using machine learning techniques and data analysis and data analytics techniques, you can actually start to predict when these pieces of kit might fail, for example. And so, you know, you can develop a predictive maintenance schedule to avoid having a piece of kit breakdown, for example. Okay. I guess I should stop there. Are there any questions? I know I've talked a lot, but are there any questions so far? Because what I'll talk about is just a couple case studies, and then, you know, kind of that would be it. So do we have any questions so far? Okay, cool. So one of the first case studies I wanted to share was this was a project that I did when I was very new, if I could go back, I would do certain things differently, obviously, but it was pretty cool. And it involves unsupervised learning, which I'll talk about a little bit more again. But it's multi-attribute seismic analysis with k-means clustering. So a lot of words, I'll go through them, as we get into it. So in exploration, as you know, you have huge volumes of seismic data that are analyzed by exploration geologists, geophysicists, whatever, and they're under usually time and also resource constraints, right? Because the company needs to make a good decision by, X date. Are they going to bid on this block or not? So machine learning, as I said before, enables computers to learn from data without being explicitly programmed. And it addresses the two major challenges that seismic interpreters might face, when analyzing this seismic data. So one, parsing huge volumes of data, and two, understanding the relationships between different types of data. And what I have here would be, this is just one, I think it's like one inline cross line from a seismic survey, but it's showing you the different types of seismic attributes, and these are 3 of hundreds, so just 3 random ones. But the geophysicists will have to, look at these things, to kind of apply their traditional techniques in order to come up with in order to find patterns that might indicate, okay, hydrocarbons, for example, may exist there. Looks like gibberish to you and me, but machines can analyze the relationships between these types of attributes, very, very easily. Right. So in this project, I worked with a geophysicist because I did not have domain knowledge, and don't remember what domain knowledge was, knowledge of a particular topic. So I'm not a geophysicist. So I worked with a geophysicist to come up with a combination of seismic attributes that could, for example, predict where a DHI or direct hydrocarbon indicator could be, right? In this, and basically I used those attributes and inputted them into a k-means clustering algorithm. I'll talk about what that is in the next slide. But so basically I'm giving all this data to this specific algorithm in order for it to give me the probability of basically the presence of a direct hydrocarbon indicator being at a certain location. And then I also incorporated saturation log data in order to generate a 3D saturation model. So a 3D model that's showing you, oil and, I think it was gas and water saturation for this particular area. So in case you weren't sure, but a seismic attribute is just a quantity derived from seismic data. So it's literally just a number. Then you have seismic attributes that I use that they're just listed here. Don't need to know what they are. And you can actually see here that this is a flat spot, which is a good indicator of contact. Anyway, so what is k-means clustering? Right, so it's a type of unsupervised machine learning algorithm. So it identifies natural clusters or patterns in the seismic attributes that I would have fed into it. And each data point in the test seismic volume that I had was allocated to one of those clusters or one of those patterns by the algorithm, as you kind of saw in the little animation, right? So if you can imagine that each point is, so this is like a feature space. Each point is a certain combination of all these seismic attributes that I used. And these points would then be assigned into particular clusters, meaning that, this cluster, all the points in it are more similar to each other than, say, this cluster or this cluster or this cluster. So that's how k-means clustering works, at a very high level. And as a result, I got 40 clusters that were generated by the k-means clustering algorithm, right, based on the seismic attributes that I used. Only 6 of those clusters, again, going back to my geophysicist, only 6 of those clusters or patterns related to geologic features of interest, such as the top of the sand or the base of the sand or a flat spot DHI, right? So you can actually see here that cluster 15, for example, actually referred to the flat spot here, for example, and cluster 20, the data points in cluster 20, kind of outline this sand, for example, right? And then after that, so I said, okay, only the points where it was most likely that those points actually belong to the cluster, those were retained. And as a result, looking in 3D space, I got 3 distinct geobodies that actually did represent three sands. So the seismic attributes were then linked to fluid saturations, and then I basically use a saturation log to extrapolate the gas and water saturation across the geobodies. And the final result was, you can see kind of red represents gas and blue represents water, but basically the result was a geologic model that matched the accepted geologic interpretation. And the key takeaway from this, I know I'm kind of coming to you with a lot of new words, but the key takeaway from this is that for a human to do it, it might take, a couple months. But talking about this kind of initial screening, in order to maybe come up with some saturations or whatever. But it takes significantly less time for a machine to do it, right? So again, remember, the k-means clustering algorithm is finding patterns in the data. And in our case, these patterns may refer to things like a sand, things like a gas-water contact, for example. But the fact is that the machine can find these patterns much quicker and can even find patterns that may not be obvious to, the geophysicists, for example, at minimal incremental cost, because we already had that seismic data. So it's just to show that, for these kinds of workflows, kind of where you're processing large amounts of data, trying to find patterns, machine learning could potentially be a good supplement to purely human workflow, for example. Right, so the second case just refers to, and it's very different. And I guess this should highlight the fact that, with data science in the petroleum industry, you literally could be, there's so many different applications. So in this case here, it was using computer vision. Again, computer vision meaning teaching a machine how to see, quote unquote, see or, kind of interpret an image. It basically involved using computer vision techniques to be able to detect the fueling sticker on some BP aircraft. And why is this important? Because a fueling mishap is a huge safety, has huge safety implications. So besides cost-wise, you see here the business values, kind of $1.2 million in consequences. Even more importantly, it's a safety issue if the wrong fuel is put into an aircraft. And so the goal of this was to be able to have an app on your phone where you take a picture of the fueling sticker, and then the operator will get back a response saying, okay, this is jet fuel, or this is aviation avgas, or whatever. Right? And so remember the steps of the data science process. So it started with acquiring the data. In this case, we limited the number of real images that we had in order to train our algorithm. And that was because if a new fuel came about, for example, you wouldn't have a ton of photos with that fuel sticker. And so what we did, because our training data set was so small, is actually created synthetic images, right? So basically you go in Paint and, you know, from the few images that you had, the 27 images, cut out the foreground, which would be, for example, the fueling sticker, cut out the background and Paint again, which would be, you know, the actual plane itself, the aircraft itself, and then use this workflow called CocoSynth to generate new images with, you know, a new fuel sticker and then background, for example. Then we moved on to preparing the data. So you can see here, because the images were taken by fueling operators, sometimes you might have a finger in the image, sometimes, you know, it would be very blurry. So basically what we did was carried out multiple processing steps. So, you know, sharpening the images, converting them to binary images, i.e. black and white only. Yeah, so just pre-processing the images so that the algorithm, which in this case was a neural network, but that the algorithm would be able to more easily use these images in order to learn, right? And then, okay, so analyzing the data. So in this experiment, you know, we tried multiple techniques. Again, you don't really need to know what these mean, but just know that during the experiment, multiple techniques were tried. There were multiple failures, and I guess that's the reason why you know, this part of it is iterative. Some things just don't work, for example. And then of course, you know, at each time we would evaluate the model. And you can see here this is this image here is called a confusion matrix, and all it's doing is telling you how many images your algorithm predicted right versus how many images your algorithm predicted incorrectly. Right. And then of course the last thing would be to act. And last but certainly not least, right? So it's about going to the stakeholders saying, hey, this is a model that we've developed. It has, you know, 90-something% precision or accuracy. We also developed this app, for example, that you have on your Android device, that you take a picture and you're able to get that fuel, you know, what the fuel is based on the image, you know, and so here you go, please deploy it, or we work with you to come up with a deployment strategy. So yeah, that was that project. Okay, I was going to talk about this one, but to be honest with you, just based on the time and also the fact that I want to leave time for questions, I'm going to skip it. But the last thing I do want to show you is this, which I think is kind of cool. I have a video and I'll play it in a little bit. But the last use case is around shaker image recognition, right? So again, similar in that we're using computer vision, but in this case, it's to analyze the cuttings or the solid material that is coming out of that's returned to the surface from the circulating drilling fluid, right? So during drilling, you basically have the mud being circulated through the system, right? So it's going into the hole and coming out at surface. And at surface, this drilling fluid is passed over these shale shakers, which essentially there's like a mesh or a filter, right? So basically the mud would then go through or is recirculated into the hole, but then what you're left with is a solid material. Now this solid material can tell you a lot about, you know, what's going on in your hole, for example. So it can tell you, you know, if your hole cleaning is poor, but you need good hole cleaning to ensure that you have good wellbore conditions and you're minimizing your non-productive time during drilling, for example. It also allows you to accurately calculate, it allows you to kind of calculate volume flux more accurately, being able to identify your cuttings allows you to assess borehole cleanliness, for example. So it can be used to assess the quality of the hole. For example, it could be an early indication of cavings where, you know, the rock has splintered from your borehole wall due to instability, which again could you know, could have kind of disastrous consequences. So being able to analyze these cuttings real time is very important, and usually a human will do it, but it, you know, being able to do it kind of real time just via the images or the video that's provided would be a much more efficient way of analyzing these cuttings. And I should apologize. The images that I have here, there's no mud. I mean, you're probably wondering where the mud is, but these are some. This was an experiment that was done, and they were just these cuttings and no mud, kind of used during the experiment. But what I wanted to show you is, and let me just see if it'll work, because when you try to do stuff real time, it doesn't work. But what I wanted to show you was kind of this was an experimental kind of analysis that I came up with in order to be able to track the cuttings as they moved along the screen, right? So what you could see is, and it's not very good, don't get me wrong, this is one of the first attempts, but I just wanted to, and again, this is with open source software, but basically what you're seeing is the program is kind of detecting, and it's not detecting all of the cuttings, obviously, but it's detecting some of the cuttings, and you can actually see them better here. And in the background, the program is kind of analyzing the area that's taken up by the little green contour lines, right? So if, for example, you move from like this size cutting to this size cutting, you should see kind of an increase in the average area of the cuttings. But yeah, I hope y'all are actually seeing this video. Please just let me know if you are on seeing it and it's not making sense. But anyway, yeah, this is one of the first attempts at trying to detect the cuttings on the shaker bed, and it's an ongoing project. But yeah, just thought I would highlight that. So I guess the last thing I wanted to talk about, if any of this was interesting to you at all, there is a traditional path to becoming a data scientist, which is bachelor's degree in some math, physics, computer science, some sort of field like that. A lot of people do master's degrees in stats or data science or related field. A lot of people have PhDs. And then, of course, as I mentioned, domain experience is important, right? So if you want to, for example, do data science in the healthcare industry, you should probably learn about that. In the oil and gas industry, you should probably know a little bit about that industry. So that's the traditional path. What was my path? Yeah, not anything like what I just said, right? So as I said, I have a BSc in chemical engineering. I have a master's degree in reservoir engineering. But what I think is that, at least with these things, you develop kind of an analytical mind. The stats and the math skills were there because of that. But I guess what's important is, I did have experience as a reservoir engineer, so I did know to some extent the domain, and I guess all this to tell you that becoming a data scientist, it's quite an accessible, I would say, yeah, it's quite an accessible field to get into. And I know a lot of you all have kind of that geoscience, that kind of petroleum engineering, geoscience, reservoir engineering background. And if you are interested in becoming a data scientist in this industry, then yeah, as I said, it's very accessible. There are kind of online learning platforms that I've used heavily. So things like Coursera, Kaggle, Udemy, where you can develop your coding skills, your data science skills, for example. All of this can be done online, or of course you can get a master's degree in data science, for example. But really just wanted to emphasize that yeah, it's very accessible, and you can start today if you're interested. There are resources that are available to you, right at this moment. Anyway, and that is it for me. I realize I've left, I don't know, is that 5 minutes for questions? I know it was a lot of information, but guys, yeah, if there are any questions, please feel free to talk to me now. So thank you very much. I know it was a lot, guys. I think I've stunned you. I'm so sorry.
It was a really good presentation, Ms. Hassanali. And so now we'll be going on to the questions and comments section. If you would like to have your questions asked, you can have maybe a few options I can present to you now. The first option is asking the question using the chat box option where you can type your message and I can read it to Ms. Hassanali, or you can use your microphone. And the last option is if you don't want to ask your question here, maybe you can even email it to the UWI SPE email and we will get it across to Ms. Hassanali to get the question answered for you. So you can go ahead and ask questions or make any comments now.
One thing I will say, just to jump in, is you can even, I'll put my email address in the chat box. So, you know, you can even ask me directly if you want it. So I'll just put it in the chat box now.
Hi, Kadija. So I don't have a question, but I just like to say thanks so much for this presentation. You know, a lot of presentations don't include, you know, the case studies and exact applications of, you know, data science. So it's really nice to get some examples to, you know, further understand how useful it could be in the industry. And especially this slide, because, you know, everyone takes such different parts to end up to, you know, their current rules. So it's nice to see that, you know, possibly there's some flexibility to getting into, you know, a career with data science. So thank you.
No problem, Mikhail. I do remember you.
Hope you're well.
No, but I do appreciate that comments. And yeah, I just wanted to emphasize that it absolutely is very possible to start, you know, 5 minutes from now, really on your path to getting more data science skills if you are interested in it. And actually, I will put into the chat box some very good resources as well.
Thank you.
Hi, Kadija. It's Paul.
Hi, Paul. How are you?
I'm all right. Great presentation. I have 2 questions, simple questions. The algorithms that you all use to put your data into, are they developed in-house in BP?
That is an excellent question. And I would say the majority of the time, no. Or at least from what I've seen. So let me preface that with, from what I have seen, it's a lot of out of the box algorithms that are used, for example. Yeah, I would say so. So, you know, looking at frameworks like TensorFlow or frameworks like PyTorch, or scikit-learn, for example. So just those kind of standard out-of-the-box machine learning libraries are the more popular ones from what I have seen, I would say. Yeah.
So based on the outputs that you're looking for, that's how you really choose which of those tools that you want to use for your analysis?
Excellent question. So I would say it. So I would say, well, one of, yes. So the outputs that you're looking for would play a part in it. I would say an even more important thing to consider would be the type of data that you have, right? So for example, if you have images, you tend to use something like a convolutional neural net, so you do some deep learning if you have to analyze images. Whereas if you had, say, like a table full of numerical data and you wanted to, for example, predict, I can't think of any examples, but if you could also do something as simple as like a linear regression, you know, then you would just use a linear regression algorithm instead of a deep learning neural network. So I think also the size and the type of data that you have would also play a part in, you know, what algorithm you would choose to analyze it, in addition to what outputs you would want as well. Yeah.
So the interpretation really comes after you do like an analysis. So you try to see what the data is saying afterwards.
That, again, great question. So there's a step in the data science process I probably didn't explicitly talk about here, but it has to do with like exploratory data analysis. And you can literally Google it. There are tons of resources around it, but it's exactly what it sounds like, exploring the data. So you might, for example, use some statistics techniques like computing correlations, for example, between variables before you would even try an algorithm, right? So you do explore your data in order to understand it before you try certain algorithms. However, to your point, after you get results, you will analyze the results and try to interpret what the results mean. And that actually brings up another great point, which is that in the industry, it's not in, and I guess in any industry, but looking at oil and gas, is not enough to tell the VP of drilling, this machine learning model told me to put a well in this location, right? So being able to explain your model and model interpretability is understanding why the algorithm is doing what it's doing is also a kind of a field that is emergent, and it's extremely important, because if you're going to base business decisions on data science, you need to be able to explain why your algorithm is giving you the results that it is, in order for people to trust what the results are, if that makes sense. So basically, you do an interpretation at the start, you do an interpretation during, you do an interpretation at the end. You're always looking at the results, you're always looking at the data and trying to wrap your head around it, So.
But I guess that makes sense, because it's also an approach to de-risking, right?
Yep.
De-risking.
Yep.
So it's just one of those other supportive, I guess, or decision-making tools that would make you more confident in doing a certain thing.
Yes, that is an excellent way to put it. Yep.
All right, so one last thing, right? The k-means clustering. Is that built into the tool that you use, or is that separate?
No, that's built in, and I think I used scikit-learn. I'll put it in the chat now, but it's Python. So I should say I do most of my, I do all of my coding in Python, and scikit-learn, I think I spelled it correctly, is the kind of built-in library or a built-in library, I should say, that has like a lot of the machine learning algorithms available to you. So again, as I said, out of the box, straight from this library. And I will say, okay, so I'm probably making it sound as if there is some like parameter tuning and stuff involved in it. So there is some work involved, but you don't have to start from scratch and build this algorithm from scratch. There are good open source frameworks and libraries available.
Right. Cool. Thanks so much, and again, thanks so much for your great presentation.
No problem at all.
Kadija, this is Rafi Hussein. Once again, excellent presentation.
Hello, Professor Hussein. How are you?
I'm fine, thank you. And you?
I'm doing well. Thank you very much.
So, for the interest of our students, we have data analytics and data science. And data analytics involves machine learning and artificial intelligence in order to look at trends and make decisions. Whereas in data science, you have those who look at algorithms and models to look for patterns. Would you say that these are two separate career paths? And if one can do the function of the other and vice versa, just for the interest of our students? Thank you very much.
So it's a good question, and I will admit that I myself sometimes struggle with understanding like the difference between data analysis versus data engineering versus data science. So there are differences between them, right? I would say that a data scientist is required to understand data, or like data analytics does fall under, I would say, data science. So with data analytics, maybe the focus is more on kind of looking at historical data and yeah, maybe understanding the context around historical data. Okay, fine. Data science might focus on, as you said, more predictive modeling. But I do think that a data scientist should, for example, an exploratory data analysis. Exactly, it has data analysis in it, if that makes sense. So data scientists should be good data analysts as well, in my opinion. I would say that, and I would say a good data analyst also has some knowledge of maybe the data science algorithms as well. I would say that they're not like mutually exclusive. I actually forgot your question. I'm not gonna lie. in terms of career path.
You're in the right path. Whether they are separate career paths or one can do the function of the other and vice versa.
Right. I would say that they are not mutually exclusive career paths. I would say a good data scientist should also have the skills to be a good data analyst. So they're not mutually exclusive. However, on the flip side, in BP, for example, there are people whose titles are data analyst and people whose titles are data scientists. So the skill sets are similar. Maybe a data analyst might be more proficient at working with data visualization tools like Power BI, for example. They might do more kind of classic statistics or something, whereas as you said, the data scientist might again be more familiar with the algorithm, etc., etc. I would say that a data scientist should be a good data analyst. If yeah. And again, I don't think they're two separate. That was very confusing.
Yes, thank you very, very much. So just for the interest of our students, I want to mention that in data analytics, use hard data. The more data that you have, the better you will be able to train your machine to do the prediction. It does not use equations that you may have seen in your study. Those equations have assumptions to it. There are no assumption in data analytics. It uses hard data. Full stop. Thanks, Kadija.
Can I comment on something there, please? Am I allowed to make a comment? Hi.
Yeah, I mean, I do. Yeah, sure. Please do.
So Kadija, you're right, and Professor Hussain, you are also right. In some reading that I had done recently, data analysts fall under data science. So data science is a much more broad field. So data science is really expected to be a good data analyst, but a data analyst has a more specific role. As Professor Hussain said, they deal with hard data and not so much equations and algorithms as such. And that is because data analysts, they know what they're working towards when it is they have data. They're trying to find a specific result for something. Whereas data scientists, they don't even know what question they're trying to answer yet. They're just trying to understand the data that they have. And that is one of the big distinguishing features between those two roles. So data analysts are tied more to providing results for specific business decisions, if that makes sense to you.
I will say though, that forming a good kind of hypothesis at the start of a data science project though is very important. So yes, there is some exploration when you're talking about exploratory data analysis and all that stuff, but I guess it is where there is a specific goal in mind, I should say. And completely agree with both of you that with data analysis, it's hard data. You're looking, it's very specific. all of that, but there is sort of a guiding question that needs to be answered in a data science project as well. Like it's very rare. I've actually never seen it where, you know, you just have some data and you're just analyze, you just, you know, kind of explore it or run algorithms on it. Like it is, the project is designed with a specific goal in mind. Yeah, but maybe not as, it's not maybe as hard and fast and specific as, you know, what a data analyst would be expected to produce, but it's definitely guided by a specific question that needs to be answered. Yeah.
So this will be the end of our questions and comments session. Sorry. So thank you very much, Ms. Hassanali, on answering the questions. Now I will just go over some announcements I have before I wrap up the session, right? So just before I move on, if anyone has any more questions, you all can always email the UWI SPE email address, and we will get back to you all after sending it to Ms. Hassanali, right? And so just before we wrap up the session, I would like to just go over some important announcements that we have. So the first announcement being that the UWI SPE Student Chapter, we held an essay competition that began on the 16th of July, and all submissions were received by the 20th of August, right? And we would just like to appreciate all the submissions received, as this has been a very successful essay competition. At the current moment, we have the judges, of course, marking and judging the essays, and we will be releasing the results by next week, Wednesday, which is the 1st of September. And as you can see on the right-hand side flyer, that's it. Those displayed are the prizes. So to the right of my screen, we have on September the 2nd, the Society of the Petroleum Engineers Trinidad and Tobago chapter will be hosting a virtual talk on solar energy in Trinidad and Tobago. And now with regards to the flyer on the left, on the 9th of September, Professor Hossain and Professor Jupiter will be hosting a virtual seminar on the suggested energy transition policy for Trinidad and Tobago over the next 50 years. And this virtual seminar will be followed by new program proposals for the Petroleum Studies unit. And lastly, just to get onto the Petro Bowl, the UWI SPE Student Chapter placed 3rd overall in the Petro Bowl regional qualifiers in the category of the Latin America and Caribbean region. Now our team will be representing the chapter at the finals, which will be held in September, right? That's next month. And persons interested in viewing the competition live can do so via YouTube. That's the end of our session. I would just like to thank our guest speaker, Ms. Hassanali, for taking her time to facilitate doing this session with the UWI SPE Student Chapter. And I would also like to thank all the other attendees for coming out today and making this event a very successful one. And that's it for today. We do look forward to seeing you in our next SPE Student Chapter virtual technical talk. Thank you.
Okay, thank you so much for having me. Have a good weekend, everyone. Bye.